这是咱的声音。
Hello， 听到吗？哦，应该 OK。
陈老师您好。
喂，早安，你好，董老师
陈老师
你
您好，可以听到您说话，这边特别清晰，效果很好。
哎，那么就好了。我再宣传一下这个活动，在这个 moment。
好的，谢谢您。那我们稍等一下，陈伟强老师。
啊，好，等我们今天的主席。
好的，谢谢您。那我们稍等一下，陈伟强老师。
啊，好，等我们今天的主席。哎，陈老师 ，Hello。
陈老师好。
嘿，董老师好，不好意思，刚才
才华老师也上线了。
哦，好
，OK。
大家好。
陈老师好，谢谢二位老师。我怎么用这个？可以用这个背景呢？看一下。
陈老师在设置里面。
是吧？
设置里面左侧第5个。
现在看到了吗？
可以看到，陈老师。
OK， 好的。
陈老师，那我们可以开始了，谢谢2位老师，感谢陈老师。那下面就交给3位老师了。
Okay, so I also have some slides to share. Okay, so welcome everyone. Welcome to this online forum organized by the Journal of Frontiers of Engineering Management. So this is the 39 or 36 of this series of the FEM forum. And my name is Wei Qiang, and I come from the Institute of Urban Environment, Chinese Academy of Sciences. Today we are going to have 2 speakers for this online forum. And this forum is based on a special issue we organized for the journal last year. That is for resilient, sustainable, and equitable cities urban management. So on that, for that special issue, we actually have 5 guest speakers, and that special issue already has 5 or 6 papers, I think, published there. So one of our speakers, Dr. Hua Cai from the Purdue University, is one of the guest editor. And I'm going to quickly introduce to you these several papers. So the first paper is on urban agriculture as nature-based solutions. And this is actually published by Dr. Yong Guanzhu and Faith from our institute. The second one is from Professor Faith Chan, who is also a speaker for today. And this paper is about the development of roadside green swales in the Chinese Bond City program. There is another paper that talks about urban how to build safe, resilient, and sustainable cities, but with focus on urban constructing wetlands. And the first one is on the efficiency evaluation of government investment for air pollution control in the Beijing-Jingji city clusters. And this is from somebody from Beijing. And the first paper is from Dr. Hua Cai from Purdue University. So I think I just quickly go through these several papers. Okay, I forget another paper that from this on energy rebound effect, but it's from Professor Cha Dongnan from Nanjing University of Astronomics. But she will present next time. So based on these several papers, we are organizing two FEM forums. And the first one is today from 10 a.m. to 10:30. So today we have Professor Hua Cai from Purdue University and also Professor Faith Chan from Nottingham University in Ningbo. We will have each speaker speech for about half an hour, and then we leave another half an hour for discussion. So that is the quickly introduction of this special issue. So let's welcome Hua Cai to give the first speech, and then after her will be Faith Chan. Hua, are you ready?
So let me share my screen first. Can you see my slides?
Yes, clearly.
Okay, great. All right. Good morning, everyone. Thank you very much for spending time with us today. And it's my great pleasure to share our work that was published on the Frontiers of Engineering Management. And the title of the paper is Understanding the Demand Predictability of Bike Share Systems, a Station-Level Analysis. So the motivation of the study is that shared micromobility that includes bike share, shared e-scooters, shared e-bikes has been growing significantly over the years globally. And the demand prediction is one big important part that we need to do in terms of not only strategically planning where to build these systems, but also to operate them from a daily basis. And there has been many efforts to develop prediction models to predict the demand at different levels. And here just shows some examples of efforts building different models try to predict the bike share demand. And by the way, in this paper, we use the bike share systems as a case study, but the approach could be applied to other systems as well. For example, shared e-scooters, e-bikes, and other shared mobility as well. So when we have these prediction models, the way we do it is we will develop one model and then evaluate the performance of the model at the aggregate level, which means the system level. So by doing this, we achieve overall system level better prediction performance, but we actually neglected the station-to-station variation and the differences. What we want to do in this study is to look at, okay, at the station level, to what degree can we actually predict the bike share demand? So if we have bad performance, is that because we don't have a good model, or is that because the demand at that station is inherently hard to predict? And then if we can use some predictability metric to measure the randomness of the demand, can we use that predictability metric to bond the predictive model performance? Basically, what are the relationship between the prediction model results and the predictability that we estimated. And then the third research question or research gap we want to identify is for the systems that we don't have data for, can we use some of the city-specific features to estimate the predictability of the demand? So our approach includes three parts. Number one is we want to establish some predictability metric at the station level. And then we will build some predictive models to evaluate the relationship between the performance of the predictability metric we developed and the results of those predictive model performance. And then we will identify whether we could use some of the time invariant features from the city structure and layout to estimate the predictability at each station. So to do this, let's look at the part one first. Okay. So the research question number one is, to what degree can we predict the demand? In other words, how much can we predict the demand reliably? And that the demand predictability really depends on the randomness of the demand at the individual station level. So what we want to do is leverage information theory and to use entropy to measure the demand randomness. And then once we have the entropy measured, we can calculate the predictability. So specifically, we look at three types of entropy. So if we have some observation of historical demand of bike share use at one station over time, such as the figure shows here. Okay, so over time, we see some demand variation over time, and at different observation phases, the red dots represent the data we captured in terms of different demand use. So the first type of demand, the first type of entropy is random entropy, which only measures how many unique demands status we would observe. So in this example, although we have 7 observations, 2 of the demands are the same. So we only have 6 unique demand levels. And then the second type of entropy will record not only how many unique demand status we have, but also how often do we have. So in this type of entropy, those 2 demand status that have the same demand, we will know the probability of them to occur is higher than the other unique demand status. And then the third type of entropy is what we call the actual entropy. It not only measures the unique demand and also the frequency that they happen, it also captures the sequence of the demand status to happen. So in what frequency we would have this level of demand change over time. So as you can see, the 3 types of entropy, they increase by the level of information that they are encoding. So the more information we encode in the entropy, the more computational intensive it is to calculate the entropy. And once we have the entropy, we can then measure the predictability. So here I'm going to skip the mathematical proof, but you can look up the literature here that shows that with the calculated entropy, we can then solve the predictability bound, maximum predictability of that demand based on each type of entropy we have. So as a case study, we use the DV bike share system in Chicago as a case study, and we use 1 year of data to capture the seasonal changes over time. So to observe the demand, here as a baseline, we use a 4-hour interval as the baseline condition, but I will show you some of the sensitivity testing using different time intervals later as well. So every 4 hours, we would record the demand use at each station, and then we measure what is their entropy based on our 3 types of entropy definitions. So here the green curve represents the random entropy, right? And then the yellow one represents the actual entropy. So as you can see here, when we encode more information, moving from the random entropy to the actual entropy, our value shift to the left. Basically, the entropy dropped. So the more information we capture, the lower the entropy it is. So which is very reasonable. And then using the entropy value, we calculated the predictability. And not surprisingly, right, the lower the entropy is, for example, the actual entropy case, the higher the probability, the higher the predictability it is. And one thing I want to note here is the actual entropy actually have 2 peaks. So which means that we actually have 2 groups of stations. So one group of the station, the predictability is almost 1, right? These are the stations that have relatively low demand. So it's either no use or 1 use, so very predictable demand. And we have another group of the stations that have a demand value that is the predictability value that is at 0.65. Which means at the maximum, no matter how good our prediction model is, right, the maximum prediction accuracy we could achieve will be 65%. And we're going to validate this using some prediction models later. I'm trying to move to the next slide. It seems my computer got stuck here. So let me see. All right. Okay. So in the baseline scenario, we used 4 hours as the time interval. And if we use different time intervals, for example, from 1 hour up to 24 hours, so the lighter the green is, the more frequent the observation is. So here you can see that as we move to more frequent observation, the entropy reduces and the predictability increases. So more frequent observation capture more information about the stations so we can better predict the demand. All right. So now we have established some metric to measure the predictability of the demand at each station. Now we want to verify, is there any relationship between our predictability measure and the performance of our prediction model? Can our predictability value really bond the performance of the predictive models? So to do that, we used the 2 benchmark models. So one is the autoregressive moving average, and the other one is XGBoost. So the auto-regressive moving average is a model that will only use historical data to study the trend of the time series. So it doesn't rely on any actual information, just the historical demand trying to predict future demand. So a time series analysis method. And then the XGBoost is the status quo machine learning model that we use. So in addition to the historical trip data that is used in the ARMA model, we also added some actual features that include some time invariant features about where are the station, how many bus stations, subway stations, parks, etc. around the station. what are the spatial network, right? What is the station capacity? How many other nearby stations we have? What is the average distance of the station to the rest of the station to capture the station network features? And also some social demographic feature of where the station are located in terms of per capita income, population density, and also some temporal related features such as the temperature at that time, precipitation, wind speed, humidity, etc. So to capture a little bit more information than the ARMA model. So for both models, what we observe, what we use to measure the performance of the model are two metrics. So one is the RMSE, which measures the absolute value error from the ground truth. And the error we can then compare it to our entropy values. And then, because the RMSE is highly correlated to the magnitude of the station, so the more demand it is, the higher the arrow is, right? To capture this magnitude issue, we also developed this cumulative score, which measures the percent of accurate prediction within a certain number of percentage bounded by the ground truth. So in this research, we use the 10% as the criteria. So how often, what percent of our prediction is within the plus minus 90%, 10% of the ground truth to compare with our predictability metric. So the results showed that so it seems that my computer is moving slow. Okay, now it shows up. All right. So the results showed that here are the RMSE value, and the first panel are the ARMA models. The second panel are the XGBoost models, and then the later two are the cumulative score metrics. And each data point represents one station. So here, number one, what we can observe is this line represents our upper bound based on our predictability value. And you can see all the performance is below this line. So we know that the practical cumulative score across different stations didn't exceed our theoretical predictability for each of the station. So we do we can use our predictability metric to evaluate the maximum performance of our predictive model in this case. And then we also observed that there are actually some correlation between the values that we have observed. The entropy and the predictability can be used as a model-free priori estimation before we build the prediction models, right? And then we also observed that we actually have some relationship between our RMSE and our CS scores. So the RMSE follows exponential association with our entropy, and there's a logistic regression relationship between the cumulative score metric and our predictability values. So, and if we change our observation threshold from 4 hours to range from 1 hour to 24 hours, we observe similar trend. So the conclusions stay. Right. So the third part of our research then is to think about, okay, so we have demonstrated that we can use these predictability metric as a priori estimation or how good our model will perform, okay, the maximum level of performance. But when we expand our stations or when we are launching new stations, we actually don't have historical data to directly measure this predictability metric. So are there features related to the city that are not changing over time, right? Time invariant features related to the city that we could use to estimate these predictability measures. So we could estimate, okay, how good are our demand if we want to estimate the demand for system expansion or new system development. So the way we do this is we use similar features we have included in our XGBoost model, but only those time invariant features. Because we don't know when are we going to use the station or where the station, the temperature at the time yet, right? All we know is we want to build a station here. If we want to estimate the station at the station demand at this location, how good our prediction could be. So we want to estimate the predictability of the demand at the station. So we use these time invariant features, build a random forest model, trying to predict the entropy and the predictability measures that we have established, assuming that we don't have the historical data to calculate them directly. And our results shows that we could achieve reasonable good model performance. And one good thing about the random forest model is that it will also show us which features are significant. So we could identify the important features that we could use to build these models trying to estimate the predictability for different stations. And the top 3 features we have identified is per capita income, spatial eccentricity, and parking lot. So per capita income and parking lot are actually negatively impacting the predictability. And the spatial eccentricity, which measures the average distance from the station to the rest of the station in the network. So basically give you a relative location of that station. Is that station in the center of the network or on the edge of the network? And here we can see that spatial eccentricity is actually positively correlated with the predictability. So we want to dig in a little bit to find out why this is the case. And what we find is it actually has a lot to do with the location of the station. So in this map, the first figure shows the per capita income, and you can see a lot of the dense colors, the darker colors are in the downtown area of Chicago, and the spatial eccentricity is the reversed, right? So if you're on the edge, you would have a higher spatial eccentricity, and the number of parking lots is also more in the downtown Chicago area. So if we plot the entropy level, which is indicated by the color here, so the red it is, the higher the entropy level it is, you will see that where the circle is, the downtown Chicago has a higher entropy level, therefore lower predictability of the demand. So our hypothesis is that in the downtown area, there's a lot of diversity land use. So there could be more different types of trip purpose to be used in the downtown area, while the suburban areas have lower accessibility, so lower diverse trip purpose. By having this high diversity trip purpose, it will make the demand more random and therefore harder to predict. So in conclusion, from the study, we have verified that different stations across the city will have different demand predictability. Some stations are easier to predict the demand, and some are harder. But we could use entropy and predictability metric to measure the upper bound of our prediction performance, regardless of what model we use. And then if we don't have historical data, we could use some time invariant city features to estimate the randomness of potential demand to qualitatively give us a sense of how good our potential demand prediction values are at those locations. So the implications from this research is that for systems that we have already implemented, the operators could apply more frequent monitoring to capture more information to reduce the entropy of the observed demand to improve predictability. And if we don't have data, we could leverage some of the time invariant features to estimate the demand prediction accuracy to help us better expand or launching new systems. Of course, this is our first attempt in terms of evaluating the predictability of bike share system demand. There are many more additional research can be done here. So first of all, we have only done this in one city, one system, the Chicago bike share system, right? We could do this in many different systems to verify this feature and also evaluate, well, do we have a transferable same time invariant features that we could use to estimate the demand predictability in different cities, or does each city or each system have their own set of features that associate with the demand predictability metric? And then here we have a very fine scale analysis at the station level. But potentially, we could also make this the temporal scale finer as well. Maybe at certain periods of the time, we could predict the demand better than the other period of time. So we could add in more of the temporal component as well. And then we have hypothesis that the stations that have higher entropy and the lower predictability is potentially linked to the more diverse trip purpose. Potentially, we could combine this with the survey data to verify that what is the source of those uncertainty in terms of demand randomness, so we can better understand the heterogeneous trip behaviors. So we can better understand this demand predictability or unpredictability at different locations. So this work is done by a team. So here I would like to acknowledge my co-authors. And with that, I would like to thank you for your attention. And I believe we will do the Q&A towards the end. So Dr. Chen, back to you. Thank you.
Okay, thank you, Hua. Thanks very much for Dr. Chai's very fascinating talk. And so everyone, please just stay here for another speech from Professor Faith Chan. And then after his talk, we are going to have the discussion. So Faith, are you here? Okay, yeah. So let's welcome Professor Faith Chan from the University of Nottingham at Linbourne campus. He's going to talk about connecting urban runoff reduction potential of roadside bioswales and exploring community perception and engagement of nature-based solutions. Welcome, Faith.
Okay, so I share my screen.
Okay.
Is it okay? think okay, right? Yeah. So everybody can see the screen and slides, right? Yeah. And hear me? Yeah. Okay. So I just start. Just want to introduce the latest findings on the Spun Cities research, and today I'm not just speaking about the paper published, but just combined with some latest findings on the Spun City program. But I will be quick and also introduce the team that worked with Lingwon in IUE, Matthew Johnson in the School of Geography in the UK school, Fan Fang is in Civil Engineering in Ningbo, and Yao Yang-Su is in IUE Baylan Station, and Xiaohui Lu is our student with Wei Chang as well, but she is based in Xiamen and Ningbo as well, and Heng Kai Chen is also Xiaohui's supervisor in Ningbo as well. So we just start the talk, right? And just want to say I will firstly in part one speak about the paper on Bioswale, and part two will combine with some latest finding on the community perception and media analysis in the Spun City program. And some research background why we are interested to study that, because of flooding is happening quite a lot, and also a lot of developing countries and location with poverty suffers more on flooding issues. And here is the paper just published in Nature Communication by Wellbank colleagues. That shows you all the findings about most of the region that suffers from flood, normally based in the low developing countries. And this issue is directly related to the meteorological changes. And this is the rainfall diagram from Hong Kong Observatory. You can see in the normal day, it doesn't have any rain in Hong Kong, for example, in the summer. Okay, but it could have intensive rainstorm like this, like for example, just 24 hours, you can see purple color. What is that means? Is like you will have 400, 500 millimeters per 24 hours rainfall. So this kind of magnitude is the year rainfall of northern China, for example, Xi'an or northwest Chinese cities. But we got this type of rainfall for a day. So then what happens is like very obvious. We will be like this kind of scenario, like after the rain I just showed you in 2010. This is in the city center in Hong Kong, and this is in the train station as well. And so not only about Hong Kong, and for the intensive rainstorm comes because of the water cannot go anywhere effectively. And some Chinese cities like Shenzhen, Guangzhou, and Wuhan, in there, for example, here, also face the similar situation. And then before I go on to speak about those nature-based solution, Bioswale, I just want to say one thing very quickly. And because we are doing science, so we just not talking about, oh, it's too much rain and water cannot go everywhere like this, but we have data, right? So for example, in the natural situation, nothing changed in the natural environment like this picture. So 100% of rainfall will actually go down to vegetation, soil, and the natural environment and rivers. That's 100%, right? For water cycle, everybody understand, right? It's not difficult, because like when cloud get too heavy, it condense and drop the rainfall here. And then, however, we need to expand our cities for our life, for our jobs, employment, or our activities. So if you do land use changes, okay. And then there are two scenarios here. Three scenarios here. One is like rural area, you still build houses, but you normally got actually there are at least 25% like water need to go another way, because you build some houses in the rural area that grab the soil space, grab the vegetation space. So for this kind of issue, you can do something like, for example, you don't build too much houses and also scarce, and then you will offload the water, okay? Because it also like the water will go down to soil, through flow, go back to rivers, or go to groundwater. But if you do this scenario like for the small development on urbanization, we build some houses, and then you expect at least 50% of rainfall. You need to sort it out, and then because there's no trees to absorb, or vegetation, grasses, flowers, whatever you call, to absorb the water, then you need to sort it out 50% of water in this kind of small development pattern. However, like where we normally stay or we normally work in Ningbo, Xiamen, Beijing, or like Hua said in Chicago, and then there are at least 80 to 90% of rainfall. You need to sort it out because you remove everything like soil, and no space for vegetation as well. Okay, so that means like, wow, you suddenly lost like 90% of space for water. So that's why it happens like this, right? So it's quite easy to understand why urban flood happens quite serious. And there one issue that we can do is like to return some natural spaces for the urban area. So we call nature-based solution. So in China, that's the version we call Smart City program that is like promoted by the Chinese national government in 2013, exactly about 10 or 11 years before. And then this kind of concept is quite similar to America. We call no impact development. But in Europe now it's very favored on the term is called nature-based solution. And from my perspective, those terms, the function is quite similar, although the concept is a little bit different. And mainly is using the green infrastructure, or we call the sponge facilities, to retreat or restore back the nature environment and give more space for water via the vegetation or green infrastructure like trees, grasses, or permeable pavement that can immerse those water inside by geotechnical way that can restore back those water in the urban area for infiltration and actually for storage. So actually through this type of green infrastructure, it has a function that can do some purification work, on the pollutants as well for digest the urban discharge and urban runoff as well. So because of that, so we can see this is like a lot of advertisement to demonstrate people lose weight, right, from big guys to slim charming persons. So same as some area for visual fitting in the urban area. That's the example in the East Town in Ningbo. So I used to have some small enterprises and dumped farmland. So we call brownfield in American term, but we also call dump land in the British term as well in urban planning. And we store the area now, build an eco corridor for green park like this, exact the same area. So like to promote the fun facilities, and also deliver multiple functions. For example, enhance their social communities can use the park freely to enjoy as well. So, and we're talking about the urban ecosystem services that improve the environment for birds and butterflies, dragonflies, bees, to do more ecosystem services for the goods for the urban environment that merge with some concept in China latestly, like beautiful China, 美丽中国, and those issues. And then we can actually understand, for example, like today, the talk, the work delivered by my PhD student Leng Wan Nu on his paper in FEM is talking about bioswale. So what is bioswale actually? So you see this kind of thing is like here. It's the bioswale. Okay, so like what's the function of it? Yeah. So it's good question, right? Like the bioswale is very useful to get some outlet from the roadside runoff, through the drainage, and then you divert the urban runoff through the roadside to the swale, and then it has vegetation, can do the job for what? To absorb the pollutants. Okay, so something like this, like a V-shaped swale, and something like this is rectangular. Something like this is exactly in the roadside with the vegetation. So I just took this, like all examples in Ningbo, New East Town now. And I can explain more detail, like people if like you fancy about chemistry. So for example, those urban runoff, it contains phosphorus, nitrogen, pesticides, metals, from where? From the car. Like for example, the car, like I know in China now is very favored on electric car, but there's still a lot of petroleum car or diesel. So for diesel car, they will expel the exhaust pipe, from the car, right? So it contains lead as well. So this is one of the metal, and also degradation from roadside, from the tires, right? For plastic fibers from tires, and biocide protection, cigarette butts, sulfur for the transport, and oil spills, tire wear particles that say tire nitrate, fire retention. So those things actually to combine with the urban runoff that people normally not look at that detail, right? So it has this kind of toxic stuff and also contaminants, we say. So for the bioswale is very useful then, we use like Leng Wan help me to digest with this diagram. So bioswale, when the urban runoff that have so many contaminants that I just speak, right? So it will divert to this type of runoff, right? So in the bioswale, it can have the function, you build a bioswale, you don't want to infiltrate so fast. So it will allow the certain amount of urban runoff to stay there. We call retention process or bioretention process here for allow the ponds to absorb those like contaminants like we just speak about. Okay, so through this like we can do purification, and also after this, like if you absorb this and storage it, so it could give the stakeholders and the government can reuse those water for another function, for example, irrigation or recreation for the river water as well. To we join this, like we use the arrow here, right? So I just want to explain a little bit here because people may not normally understand what bioswale used for. Like some people may against the function of it because it will trap people down or something, but it is certainly built for the purpose, and the purpose is very useful. I just want to explain like this here. And so we also understand, we care about health and we want to reduce pollutants other than we sort out the urban flooding issues. So like bioswale is exactly can get some benefit to actually remove some pollutants and also enhance the ecosystem services here. Okay, so we actually can get these kind of issues. So for our study, for Lingwen's PhD, we understand, we try to see actually what the latest development on the Smart City program plus the use of those green infrastructure, especially for bioswale. Actually, just want to say in 2016, there's 30 cities that joined us on the Smart City program, including the legislative city in here in Ningbo. But also we can notice there's some familiar names that you may want to know, like what Weichang is working in German is a legislative Smart City. And also Qingdao, we enjoy the beer and water activities is legislated of Smart City. And also Xi'an, we enjoy the historic and emperor city is also the Smart City. And Guiyang, like we have another team member like Xitong is from there. It is also the Smart City as well. And some mega city like Shanghai, Shenzhen is also Smart City, and the tourist spot like Zhuhai is also Smart City, Tianjin, Beijing, Dalian as well. So that's the situation of 2018 and those issues. But now it's more Smart cities to raise their hands after the 14.5 Congress, and by the latest, like last year, 2023, is already like have 45 Smart cities legislated in China. But according to my new PhD student, Yi Zhou, now is tracing how many latest Smart city established in China. Now have 70. Like I can guarantee now it's 70. But it's not all cities in the first tier or mega city style, like have 8 million to 10 million people. For example, there are cities like, for example, Yangzhou, Hengshui, and Anyang and Foshan. These kind of cities, like we understand, or maybe it's second to third tier city that the population is about 5 million to 8 million, something like that. And also they also put their hands up on to improve the urban water system, actually, not just to sort out the flooding. As I said, I explained, actually maybe sort out the other problems, like, for example, pollution problems or greening problems or blue-green space problems. Like, for example, Lhasa, like, also joined the program, but is comparatively drier than salmon, right? Yeah. So, but it also joined the program because to promote nature-based solution, to promote beauty cities in China. There's multiple concerns for Smart cities as well. Just want to say. So we just want to promote these kind of issues, and then we try to work for this project. Like Lingwen is looking at, okay, we look at the past, we look at the present, we also look at the future. What future is like climate change projection. So how does well performance in the future? So he's looking particularly, how to like do some modeling to see, okay, in different amount of rainfall, what's the performance of the Smart city swell in Ningbo can do or can do better, so that's his focus at the moment. And then we we sort of just try to, we are not doing rocket science. We do things with a framework, right? So Lingwen, like and us, is looking at the service time and the rainstorm return period, and also the swell design, and also the soil properties and vegetation, and also funding, the money, and human activities. Will the topic support this kind of thing? And so his PhD and our work is like to design, from different rain intensity, for example, 2 years return, 5 years, 10 years, 20, 50 to 100 years return, like bigger rainfall, and how the performance of the swell, and also how the coverage of swell in this study. So just want to be quick is he used some field sport is very famous in Ningbo for the sponge facilities. For example, Chicheng Central Lake is one of the featured nature-based solution or sponge city facility that is quite famous, not just in China, but also internationally quite famous as well. And we will show some result here. So he's based on different parameters. Of course, I'm not going to explain to this, but I can send you those documents if you're interested. So based by the design from the Ministry of Housing and Development Construction, and also Water Bureau, and also the Road Development Bureau as well. So just want to say those guidance of engineering construction guidance is based on legislation. It's not making it up. And in our country, that's those legislation is very good and can trace the standard to the Western world, actually. I just want to show you the example because people are questioning, oh, China built things so fast, like it's like rocket science. No, actually not. I just want to prove it's not. We are based on a lot of legislation, and also parameters is very tight, as good as the United States and European Union. I just want to say it and prove it. And I just want to show you some result that Lingwen is doing. So he actually analyzes a lot of events during different time in the time series as well for the swell and the rainfall data. So just show you some results like here that he has done some analysis through the simulation. And also, I think we try to look future, right? So we combine with the SSP 2 to 4.5, 3 to 7.0, and also the scenario of 8.5 up to by the IPCC as well. So seeing, what does swell do to perform in terms of future, by the SSP in IPCC projection for climate change. And I think everybody wants to see some result, and actually let's keep it confidential because it's not published yet. But Lingwen is very generous, want to show you some result, right? So we found that actually the performance of swell is okay. We tried to do 2 years to 100 years, right, and also the extreme event in Meihua in 2020 September, which is like more than 1 in 100 years, like that level is 1 in 200 to 500 years return period. So for the normalized objective function NOF, we actually see the result is quite feasible, that normally the swell do okay well is in the small range, like 2 to 10 years, like return period, because it's understandable. If too much rain, actually the retention time of the swell is limited, and also will be overfed as well for this event. Okay, so I will show you the picture. And also, we want to show you that because it's very hard to read those like simulation graph or something. everything, but we try to make a very simple table to show you actually in the baseline sponge city program in what within the 1 in 30 years return period, because the sponge design of the swell and the other green infrastructure is only asked to do 1 in 30 years return period. You can do larger, you can do more safer green infrastructure by the own investment of the city government. But the construction guidance that published by Ministry of Housing and Construction is only required you to do 1 in 30 years. So for this baseline, and actually we talk about, for example, the rate of removal nitrogen can reach 24.15%. Is quite okay, 24.15 is okay to for example, to make the level 5 polluted water to level 3 actually. Yeah, so it's very quite useful by the analysis for us doing for the Ningbo data. Yeah, and then how about the future in SSP 2 to 4.5? It has 17.9%, and for SSP up to 7.0 is 18%, and up to 8.5 still have 70%. So it's doing the ratio is within 70% of the effectiveness, and the removal rate about 20%. So I think that's quite a positive news and encouraging that to prove the swell is quite useful to. Of course, we don't have capacity to do loads of contaminants but nitrogen and phosphorus is the government most concerned, because you will get eutrophication if you have the excess nutrients in the urban runoff that Ningbo face all summers, all the summertime. If you come from this region, it. Yeah. So nitrogen and those fertilizer or those nutrients thing is the government concern most, but the bioswale can do quite a good job on this kind of issue. And just want to say this kind of positive news, and also we try to combine and do more research and doing different performance, doing verification, and also justify the result, which is true or not, to reduce the error. So we just want to show you we are doing quite lots of tests and the statistical analysis. And just want to say the Meihua events that more than when the rain more than 30 years return period, it could be like that, the swell will full of water and overflow as well. It's very normal because the green infrastructure is limited, right? You cannot expect it do everything. So I just want to say those green infrastructure, you can do something, but cannot solve everything. That's my message as well. So a lot of people keep asking me, why Zhengzhou government invest a lot and then it felt like that, sponge city program is rubbish, it's useless, waste of money, waste taxpayers. Come on, no, it do a lot of good stuff, but when the climate extreme issue, we need more solutions. So I'm going to speak more, And then, but one thing is because of a lot of misunderstanding of sponge city program and also nature-based solution. So our team, including myself with Leng Wen and Situng and also the other PhD students, we work together to tackle one issue is how much understanding, public perception that people understand sponge city in the last 2 years. And then we try to do this research because in China, there's not many studies to focus on social science and the social science on the sponge city programs. A lot of people like myself doing a lot of modeling stuff or water stuff, publishing water research on those issues. But how about public? Because we're doing this for the public, right? For the community. So how community understand this is very interesting. So I work with some PhD students and also my research research student Yafeng. Now she's studying in Columbia University in New York, and we try to interview those communities in free sport like Chicheng, I just explained, and New East Town, and also the Meihua New Development area to see the differences. So we just tried to interview in there for 35 people, and from different classes, for example, professionals, retired peoples, old peoples, university students, housewives, and also urban planners, professionals, and water engineers from the government. So we try to understand what they perceive those issues and how they connect with the challenge and limitation opportunities. So we try to see if there anything that can enhance. We see actually in the sponge park, it has very key information like this. So you will see this to explain you what the green infrastructure is doing. And also, I'm not very good in social media. Everybody knows it in my team. You know, some PhD students laugh at me as well. I never use Xiaohongshu. I never use Bilibili, and but it's quite useful. Actually, my students saying, you know, order, like find lots of videos sent back to me from Ningbo government, and they put their education video in Xiaohongshu, in Bilibili, which is very interesting. I use it to teach my students as well. I found very useful. I don't normally go to there to watch those stuff, you know, because it's like we are too busy on things, but I found that the government is very smart to use these kind of things. And also that related to the next research that Xiao Hui Lu is my student with Wei Chang and also Heng Kai as well. So we try to use some alternative way to understand now, you know, how we can digest spontaneity or those things by news media. You know, and then I don't know these kind of things, you know. So Xiao Kui is the expert to do these kind of things, like by using the GDAL, GKG knowledge graph database, you know, to that database is quite powerful, like can actually absorb all the news, like real time, 10 minutes for each intervals, right? Yeah, for lots of news, yeah. And they have more than 400,000 frames as well. And of course, we don't trace all the frames, but we extract those things, like, for example, relate to urban first. So there's like 17 frames that related. So we extract, for example, flood warning and the flood protection, the road flooding situation, and those stuff. And also, we digest, like we talk about sponge city, right? We digest all sponge cities in 2016 and 20. Those, like we found about 30 sponge cities, but mainly 27 because the other 3 cities is too small. So we just found 27 like quite major cities to do the analysis on the news media and the concern. So like what we expect is really true is like large cities or larger cities have more concern on the news, right? Because the smaller cities is hard for journalists to report the latest finding on sponge cities. And we also do the legend graph as well here to explain different type of city, you know, have different kind of news media and their activities, and also the actually the reactions from 2015 all the way to 2021. And especially we found one issue, because sometimes we guess is okay, right? But we are scientists. We really need Xiao Kui to really analyze all the news to see, oh, is it because actually the flooding time in the summer, normally in China and East Asia, the flooding is different, right? In the UK or in Europe, Christmas and the winter time is the flooding time because intensive rainfall from Arctic Ocean, okay, from Arctic and Atlantic Ocean. But in this region, normally we would normally we'll have a wet season in the summertime, except the La Nina pattern, right? But normally in the summertime, because of typhoons and low pressure storms, like Asian monsoon pattern as well, from the Southeast Asia all the way, the current move to East Asia. So we have those intensive rainfall normally in the wet season. So that means we expect, me and Xiaohui and also supervisor like Wei Chang expect, it should have more attention for media during the flooding time, right? Yeah, that's true. But through the analysis, we prove that's true, right? So we show you actually for southern China, southern inland China, northern China, normally the news pattern on flooding issues will be actually accumulate and intensify in the summertime. And so I just want to say we finished the discussion and also the talk here, because I don't want to grab people for late lunch, but I just want to summarize a few points here. And the sponsorship program and MBS, those stuff is important, but it cannot do everything that to prevent the extreme rainfall. People need to put in mind, and also how much you invest normally will have bigger return. So you can do higher protection, but you need to see the cost effectiveness in mind. That is the expert. I will work more with Wei Chang's team, because Wei Chang is very good in this kind of life cycle assessment, cost benefit analysis, and also those material investment, those issues. And we also want to say something about for those issues on public perception and community engagement is very important. Government has done some proactive approach on using social media or technologies that Chinese government is really improving, because those stuff you cannot see 10 years before, when technology is not moving to this stage. But the government is working with technology step by step parallelly. And also the government cares public perceptions and their understanding and their viewpoint. So they provide this platform for them to communicate through the social media. And also increasing community engagement, we think is important, because to improve the program as well for this, But I think some issues we still need to try, some new method, for example, use alternative or use non-traditional way to manage urban flooding, like use social media to see the angles, like how can we improve something besides the normal way on flood simulation, methodological study, and those stuff, right? So I think it's very interesting that we collaborate with Xiaohui, Wei Chang, and also Hinkai do this study, and it's very important as well. And just want to say we've published some papers, including that FEM paper. Thanks for FEM give us the chance and opportunities. And also, if you're interested, I can send you some papers about public perception. That's one of the first paper we do in China. And also, we published that GDL paper in scientific report like a year before. So thank you for everybody, and if you have any question, you can ask us as well. Thanks, Wei Chang. Thanks, Chaihua. Thanks, Dong Lao Shi. Thank you.
Okay, many thanks to Faith. So now let's move into the discussion Q&A question, Q&A time. Hua, are you still here? Chaihua?
I think he's here. Yes, she's here.
She's okay. Anyone who has questions, can you just turn on your camera and so that we can see you? You can ask your question.
Hello. Hello, Professor Chen. Can you hear me?
Yes.
Thank you for your wonderful presentation. And I'm Yinghuan Chen, a student from Professor Wei Changchen's group. And my research is about the rooftop utilization. And I have learned that green roofs also have the function of elevating urban plots. And the benefits may vary depending on the location of deployment. So I wonder, how does the layout of green infrastructure affect the effectiveness of flood mitigation? I mean, centralized layout, which means construct these green infrastructures as a large block, or a decentralized layout, which means scatter them in their multiple locations throughout the city, which is the deployment may be more benefit for elevating the urban flood, and is the deployment strategy influenced by the rainfall patterns? Thank you.
I think I reply quite quickly. I think your question is very good, and then I digest your question has few layers as well. But you need to understand what the sponge design I just explained. The 2014 the government Ministry of Housing and Development, they published the construction guidance on sponge city. Actually, that is like just they still have not to move the construction guidance to the all cities catchment scale, So basically, for example, through the guidance, if you want to do a small port size through the sponge facilities in a district or in an estate, Chuan, it's okay. It's quite detailed to tell you how to do it, but maybe the government will actually change the legislation later. I'm not represent them, but for your question, is more related to actually what the Ministry of Water or concern is all about the city level on the drainage and the urban runoff discharge issue. I think I can tell you very short is like the sponge city program and port size stuff is doing well, but it really need what you're asking, like to connect with the city level overall urban flood or flood protection standard to connect together. But I think the government is doing that already. But maybe we can wait and see how they connect together. I think it's not that's easy. But I think what the Ministry of Housing and Development is doing is they try to grab all the sponge project. Now the port size working well first to demonstrate it can at least to sort out the level of this district is okay, and then move to the next step, what you're saying, to divert all the water in the whole city level. And also, I just want to remind you one thing, and the sponge city program is not telling you to sort out everywhere have 1 in 30 years return period issues, but just 70% in the city center district, So I think the government, the city government who raised the hand is working hard to do this, And then later, maybe we can see more, but this is my answer. Thank you. Yeah.
Thank you.
Okay, many thanks to Faith. So I have a question actually to Hua. Are you here? So you talk about the system of Chicago's bike sharing. Well, I think this is based on the traditional bike sharing system, right? Not the new mode like more mobile or the new ones. I wonder how this kind of like the mobile system, this style is this stack now applied in the U.S. cities, and if the whole system transferred from the traditional ones to the new system, and how your studies can be then applied, or improved to help them?
That's a great question. So first of all, the new system you were referring to is what we call a floating bike share system. So mainly there's no station capacity limit that will restrict in terms of how many bikes to be parked at the station. So basically the station will not be able to be full to have more bikes to be put in there. So within the United States, actually most of the bike share systems are still station-based. There are a few floating bike share systems, but in the US, actually more and more of the system are migrating into shared scooter system, which are floating systems. So based on our study, the approach can be applied to floating bike share or e-scooter shared systems. The main difference, one of the ways people use to study those floating shared micro-mobility system is to have pseudo stations. So basically, to make the system more controllable, we would separate the service area into grids or smaller regions, and then use that one grid or one region as a pseudo station. It's basically a station without capacity limit. So within our study, we didn't see station capacity be a key component in terms of limiting the predictability or as a prediction factor. So I think applying the same approach of using the pseudo station for the floating system could be still reasonable.
Okay, thank you. So any other questions from the audience?
Hello, Dr. Faith Chan.
Hi.
I'm Wen Yizhu. I have a question. So, as you mentioned, nature-based solution or sponge city can solve the problem to a certain extent, but very heavy rainfall situations still cause a problem, like what happened in Zhengzhou. So I want to ask that should we stick with this, or what should we do to make it work better?
Yeah, good question. Very short. I want to just want to say one thing is like if we want to improve the climate resilience as a whole, we cannot just use one side. Like for example, nature-based solution and also sponge city program and also this kind of stuff is like categorized as the prevention measure. And we need to work with the other type of elements. For example, what Xiaohui and the other people do, like to investigate people by social media or by the other analysis, how to improve the social preparedness. Preparation is important, and how the government responds to it also relate to social media as well, like how to use mobile phone to check the first situation and emergency that save your life and move, right? So and also one thing is very important as well is the recovery, because it's like for climate change like this happen, we cannot to single out ourselves saying, oh, we never get our feet wet or something, get ready. We need to be prepared. We will be fit. But once you are further, you need to know what you want, what you need to do, because like what you can do. Then is the recovery process as well, like to have maybe the first aid or the climate aid system or support system financially, that you can borrow some money, you can loan some money, or you can get some support like by insurance, or establish climate insurance, climate bond, or those kind of issues combined together. Then I think and it will work better. But if we just focus on one side on prevention, is not that is not the strategy. And also not I think not just in China for the FEM, like Frontiers of Engineers or Chinese Engineering Association. In the UK we call ICE, Institute of Civil Engineers. We concern those practices work together with engineering method on green engineering, plus gray engineering, plus those issues I just explained with soft methods together. So then I think it will enhance better or improve climate resilience. I hope to answer your question. Thank you.
Thank you.
Okay. So any other questions? 也可以用中文提问哈。
可以，我的中文还可以的。我有一个问题，那么柴老师，你做完这个 study 之后，你在美国打算有什么 follow up 的工作呢？
我们这个后续就是我当时列了几点吧，一个就是说这个只是针对一个系统的一个研究，然后我们后续也想看一下多个城市是不是这样的 pattern 都适应，以及是不是同样的一系列的这个 feature 可以用于预测多个不同城市的一个可预测性。这个是我们现在在做的，我们大概全球有收集大概200多个系统的数据。
哇，很厉害。我觉得很有趣的一个 study 啦，就是把这个交通跟用这些 technology， 我觉得这样可能帮到很多人呐，真的是不单是 logistic 方面，很多快递啊这些都可以相关 ，more effective。
谢谢飞。
OK， 如果没有其他问题，我们就请董慧文老师做个总结吧。董老师。
陈老师，两位嘉宾，特别感谢大家对 FEM 的大力支持和本期讲坛的关注。同时也希望各位老师继续关注FEM 的发展，然后也欢迎各位老师继续为FEM 带来高质量的稿件。谢谢大家。
OK， 好，谢谢董老师。那我最后再补充2条。第一呢，就是我们这个围绕上一次这个专栏，其实还有另外一期讲坛。应该是在4月初，具体时间我们再通知。然后呢，刚才董老师讲的，这 FEM 是一个非常好的期刊，因为现在影响因子已经过期了。大家如果有好的 paper， 就赶紧投稿哈，因为过了明年可能就不好投了，越来越不好投。好，那就我们再次感谢2位老师的精彩报告，以及感谢董老师，也感谢所有各位老师的同学的这个参与，谢谢，我们下次再见。
谢谢陈老师，谢谢柴老师，谢谢董老师，
好，拜拜。
谢谢陈老师的主持，董老师的邀请，以及Faith的
拜拜。OK，
谢谢大家，
拜拜。
好，拜拜。